So today we're going to demystify machine learning. We are pulling back the curtain on how computers actually make predictions, and we'll do it using Python's most powerful and popular library for the job, Scikit-learn. Okay, let's dive right in. At the heart of it all is this one big question. How do you take a mountain of raw data, past sales, customer clicks, all that stuff, and teach a machine to find the hidden signals, to make smart guesses about what's coming next? Well, this isn't magic, it's not science fiction, it's the core of machine learning. And by the end of this, you'll have the exact blueprint for how it's done. All right, so here's the game plan. We're going to start with the core idea, then we'll grab our tools, walk through the universal blueprint for pretty much any machine learning project, and then we'll put it into action. I'll even show you a few pro-level techniques before setting you up with your very first project. Okay, section 1, teaching computers to predict. Think about it like this. Instead of writing this huge, complicated rulebook on how to identify a cat, must have pointy ears, whiskers, a tail, we just show the computer thousands and thousands of cat pictures. We give it examples and just let it figure out the patterns for itself. That's the huge shift here, learning from data to make decisions. And that learning process, that's what feels like magic. Scikit-learn is the library that hands you the spell book. The spells are just algorithms designed for specific jobs. You need to classify emails as spam or not spam? There's a spell for that. Want to predict house prices? There's a different one. Need to group your customers by their behavior? Yep, Scikit-learn has a tool for that too, putting all this incredible power right at your fingertips. All right, moving on to section 2, the data scientist's toolkit. See, before we can build anything, we need to get our tools together. Scikit-learn is amazing, but it doesn't work in a vacuum. It actually relies on a few other core Python libraries to do the heavy lifting with the data. First up, we've got NumPy. You see, machine learning is pretty much all math under the hood, and computers need to do that math fast. NumPy gives us the fundamental building block for this, the array. Think of it as a super efficient grid of numbers that NumPy can perform calculations on way, way faster than standard Python lists. It really is the high-performance engine for all of data science. Next up is Pandas. Now, if NumPy gives us the fast number grids, Pandas puts them into a structure you'll get to know and love called a data frame, which is basically a super-powered spreadsheet right inside your code. Let's be honest, real-world data is messy. It's got missing values, weird formatting, columns you don't need. Pandas is the tool you'll use to load that data and just scrub it clean, getting it all organized and ready for your model. And finally, we have our visualization tools, Matplotlib and Seaborn. I like to think of these as the artist's brushes. And here's why that's so important. Before you ask a machine to find patterns, you should always try to see them for yourself first. A quick chart can seriously tell you more than hours of just staring at rows of numbers. Okay, let's move on to section 3 and see how this all fits together. We have our tools, and now we need the plan. And the best part about Scikit-learn is that most projects follow the exact same blueprint. It's a reliable, repeatable recipe for success. And this is it, the core workflow. Now, I know it looks like a lot of steps, but you can really break it down into 3 simple phases. First is the setup. You import your tools and get your data ready. Second is the experiment. You split the data, pick a model, and train it. And finally, you get the payoff. You see how well your model did, and then use it to make new predictions. This is the fundamental rhythm of almost every machine learning project you'll ever do. And believe it or not, that entire workflow really boils down to 2 key actions. First, there's .fit. This is the study command. You give the model your training data and you tell it, learn everything you can from this. It's like cramming for a test. Then you have .predict. This is the test command. You give it new data that it has never seen before and you say, okay, show me what you learned. Study and test, fit and predict. That's the loop. Which brings us right to section 4, building a predictive model. Okay, enough theory. Let's see what this blueprint actually looks like when we apply it to some real data. Now, this is probably the most important step in the entire blueprint, the data split. We take our whole data set and we hide about 20% of it. We just set it aside and we call it the testing set. So why do we do this? Because a model could easily just memorize the answers in the training data, and a model that only memorizes is totally useless on new, real-world data. This hidden test set is the final exam. It proves the model can actually generalize and find real patterns, not just parrot back answers it's already seen. So how do you choose a model? Well, it all depends on the kind of answer you're looking for. Are you trying to answer how much or how many? Well, that's a regression problem. Are you trying to answer which one, or is this option A or option B? That's a classification problem. Or maybe you're just asking what natural groups are in this data, without any labels to begin with. That's clustering. The question you ask dictates the tool you use. Okay, let's head into Section 5 and see how we can really level up our game. Once you have a basic model up and running, there are a few professional techniques you can use to make it cleaner, way more powerful, and a whole lot more reliable. So a lot of models work better if all your input numbers are on a similar scale, like say everything is between 0 and 1. The manual way to do this is a two-step process. First, you apply what's called a scalar to your data. Then, you feed that scaled data into your model. It works, but it's clunky. And more importantly, it's really easy to make mistakes, like accidentally leaking information from your test set during that scaling step. So we have this clunky, error-prone two-step process. But what if you could just kind of weld those steps together into a single, streamlined unit? A single object that handles everything in the right order every single time. Well, there is a much cleaner, much safer way to manage this whole workflow. And the solution is the pipeline. Think of it like a little assembly line for your data. You define the steps. Step 1, scale the data. Step 2, train the model, and you lock them together. Now all you have to do is show your data to the start of the pipeline and call .fit one time. The data just flows through each step in the correct order, automatically. This isn't just about being tidy. It's a best practice that prevents a really critical error called data leakage, which makes sure your model's evaluation is actually honest. Another pro move is called cross-validation. That single train test split we did is good, but what if you just got lucky or unlucky with that one particular split? Cross-validation is like getting a bunch of second opinions. It carves your data into, say, 5 different sections or folds. It trains on 4 of them and tests on the 5th one. Then it rotates and does this 5 times over. By averaging the scores from each of those folds, you get a much more robust and trustworthy measure of how your model will actually perform in the real world. And that brings us to our final section, your first ML project. We've gone all the way from a basic question to the tools, to the blueprint, and even some advanced techniques. Now it's your turn to put it all together. So where should you start? Here are 4 classic projects that are perfect. For a really simple classification task, the Iris dataset is the perfect hello world of machine learning. If you want to practice cleaning messy data before modeling, the Titanic survival dataset is a fantastic challenge. And to apply what you've learned about regression or clustering, you can try predicting house prices or finding different segments of customers. So there you have it. You've seen how it's done, you have the tools, and you have the step-by-step blueprint that data scientists use every single day. The only question left is, what problem are you going to solve first?